Hello, and welcome to a digital statistics lecture for Salt Lake Community College. In this video, what we're going to do is analyze, or we're going to go through section 10.2 for Math 1040, which is hypothesis test for a population proportion. So in 10.1, we talked about how to set up hypotheses and how to knock them down. Also in chapter 9, we talked about how to set up confidence intervals for population proportions. Likewise here, we're going to do an hypothesis test for a population proportion. In order to do these, what we need to do is verify a few things. We basically set up everything in terms of how to do a hypothesis test, but we also need to make sure that we know our conditions, because these are all going to still be based on the normal distribution. Our conditions are the same as they were from Chapter 9, and also Chapter 8 technically. We want to make sure that our sample is a simple random sample, or that it says randomness somewhere. We want to make sure np1 minus p is greater than or equal to 10. And we want to make sure that the sampled values are independent of each other. So that means that the little n is less than or equal to 0.05 capital N. Okay, a couple things of note. This value, p, when you're setting up np times 1 minus p, note that that is p and not p hat. That is very different. P hat is the proportion that we get from a sample. This p, this is the value that we'll actually have in our hypotheses itself. So make sure that you use that value instead, not the proportion that you get from the sample. That is very important. Okay, so p is for the population proportion. Make sure you do have that correctly. All right, now what we're going to do is set up those hypothesis tests. We have those conditions to check, and then what we're going to do is try to find what we call a p-value. And what we're going to do is compare that p-value to alpha, which is, if you remember, our level of significance to test for type 1 error. Type 1 error is our main concern, so we want to make sure that our p-value is going to be less than that. What that will imply is that our proportion, the likelihood of seeing something like that, is far less than the chance of making type 1 error, so we should be okay. Type 1 error we want to be really small, but if the p-value, which is the probability value more or less, the probability of seeing something as extreme or more extreme than what we saw, under the assumption that the null hypothesis was true, if that is so small or so unusual, then that would provide evidence that perhaps the assumed proportion or assumed mean actually is false. You'll see a couple examples of that. And if p-value is less than alpha, then we have statistically significant evidence to reject the null hypothesis. So that will be our condition. It's kind of like how in Chapter 4, when working with correlation values, we want to make sure our correlation coefficient was higher than the critical value in order to claim linearity. Here we want our p-value to be less than the level of significance in order to claim that the null hypothesis can be rejected. So in order to do things, in order to actually take action, we need to make sure our p-value is less than alpha. As an example of this, we have in a Zogby International Survey, 1,864 out of 2,246 randomly selected adults in the United States said that texting while driving should be illegal. Use a 0.05 significance level to test the claim that more than 80% of adults believe that texting while driving should be illegal. All right, so our requirements. 1, it says random. It says so in the first line or right there, that they're randomly selected, so we're all good. Secondly, np times 1 minus p, making sure we use the correct proportion. Note that this 1,864 out of 2,246, that will create p hat. That will create the sample proportion. But what we want to test against is that 80%. So that is what we're going to test. And that's another way of thinking about that, is that 80% came before we did any testing. That's the value that we're testing against. And 1864 out of 2246 came afterward. So we should be checking our requirements before we do any testing, theoretically. But we have a sample size of 2,246, so 2246 times 0.80, that's our p-value, times 1 minus, not our p-value, our population proportion, times 1 minus 0.80. And we can calculate what that's going to be. So 2246 times 0.8 times 1 minus 0.8. What we get is 350 359, or about 360-ish. So about 359. That is way more than 10, so we're good. Thirdly, we have adults in the United States, and we tested 2,246 of them. 2,246 is definitely less than 5% of all adult Americans, or adults in the U.S. So that's all good. All right. All three conditions are met. Now we can set up our hypotheses. The null hypothesis is, in this case, we're testing P, and the null hypothesis is that it is equal to the assumed 0.80. That's 80% of adult Americans believe that texting while driving should be illegal. However, for the alternative, we want to test that more than that is true. So we want to test that greater than 0.80 is actually true, based on our sample results. And our sample results yielded P hat was 1,864 out of 2,246. If I just look at what that is, what P hat is, 1864 divided by 2246, that is 82.9%, or about 83%. That is higher than the supposed value of 80%, but our question is that significantly higher? That's going to be our question here. If we draw this, draw a normal curve, our supposed value of 0.80 should be in the middle here, and we want to see if 0.83% is weird enough. So 0.83 is somewhere up here, and what we're going to find is this percentage. This percentage, the area of that tail, that is going to be our p-value. Our probability of seeing something as extreme or more extreme than what was observed, that 0.83 value. Okay, so that's what we're really looking at. Now, when we do this, we can compute the test statistic and the p-value either by hand or via the calculator. I'm going to say if you want to do this by hand, go for it. We have the formula here. You have your p hat value, which is the one that we got. P sub 0 is the one that would be in your hypothesis. And then you divide that by the standard deviation with p sub 0. You can find that z-score. You can find what the p-value is based on the table 5, which we used back in chapter 8 and 7. If you want to use that, you can. What I'm going to do, I'm going to forego that. And I'm going to do it, oh yeah, here's that table here if you also want to find it here. I'm going to do this with our calculator. Okay, there's not an extra space. I thought there would be. All right, so the way that we're going to do this, so I'm going to forego this. I'm going to do this with our calculator. And in our calculator, what we're going to do is go to the same section we did in chapter 9. So we're going to go into stat. We're going to go into tests, which makes sense because we're doing a hypothesis test. The kind of test that we're doing is on one proportion. So the program that we want is likewise one proportion z, notice that we're still working with z, in this case, test. That should sound very familiar. In chapter 9, we worked with one prob z int. Here we're doing one proportion, because we're only testing one proportion against the population, z because it's based on the z statistic, and then test because we're doing hypothesis test. In chapter 9, we had one prob z int for confidence intervals. If we look in test, we see one prob z test is there on number 5. And in number 5, it'll ask us for a few things. It'll ask us for p sub 0. That's the value in your null hypothesis. That was our 0.8. And then it'll ask us for x and n. So that's going to be the two values that set up the sample proportion. 18. Whoop. I'll just clear that. Backspace. 1864. And a total sample size of 2246. The fourth one will ask what direction is the alternate hypothesis. Our alternative hypothesis was greater than, so we're going to use the third option there, greater than. Whoa. Okay. We're going to use the third option here, greater than. Make sure that that one is appropriately highlighted. If you have an option for a color, that's fine. That's for drawing purposes. Some calculators have that, some don't. Either way, you don't really need it. We just need to calculate. And what we get is our test statistic. We get Z. Z comes out to be 3.54, which means it's 3.54 standard deviations above the mean. That should seem rather large to you, and it is. That is really far away. Likewise, we get our p-value from that. We get a p-value that's really small. It's 1.96 e negative 4. 1.96 e negative 4, which, remember, that means scientific notation. That indicates that our value is 1.96, and then you can move the decimal 4 places over to the left. So this is the same as 0.000196. So that's our p-value. And in this case, we're going to compare that to alpha and reject it if it is less than alpha. In this situation, we have alpha being right here, 0.05 significance level. That is alpha. So, since alpha is 0.05, that's a very common level to use for alpha, we have that the p-value is definitely less than alpha. Sometimes you'll even see a double less than sign if it is significantly less than, but we can just keep it with 1. Since it is less than alpha, that means that we have enough evidence to reject the null hypothesis. So we have enough evidence to say that, that the proportion is actually greater than 0.8, not 0.80. And we're going to put that down here in our conclusions. Because alpha, or I'll say, because the p-value was less than alpha, that means that we reject the null hypothesis, and there is enough evidence, or there is sufficient evidence to claim that, well, let's look at the original situation to see what we claim. The original situation was that adults in America said texting while driving should be illegal, and we're trying to claim that more of them believe that it should be illegal. So what we showed, we rejected the null hypothesis that was 80%, and we have enough evidence to claim that that more than 80% of adult Americans believe that texting while driving should be illegal. So that's what we're looking for. All right, that's a hypothesis test. We did all the parts. We checked to see if it was normal. We set up a hypothesis. We found the p-value using our function 1prob_z test. And then with that p-value, we compared to alpha and drew our conclusions. So like a 4 or 5 step process. Let's do another example. This one should sound familiar because it's using similar information. According to QSR Magazine, Chick-fil-A has the best accuracy of drive-thru orders with 94% of drive-thru orders filled correctly. So 94%. That is going to be our P, or technically P sub 0. The manager of a competing fast food restaurant claims that her drive-thru is more accurate than Chick-fil-A. Now, we had that before, but we didn't have the actual information. We have that she did a random sample, or he or she did a random sample of 224 drive-thru orders, so that's N, and found that 216 were correct. So that's X. That's how many of the total were correct. We also have alpha's 0.05 level of significance to test the claim. So we have that yet again. Okay, so it doesn't say to check the conditions, but we should address that real quick. It says random right here in the description, so that's good enough for that condition. 224 drive-through orders is likely less than 5% of all drive-through orders, so that's probably okay. And if we check NP times 1 minus P, making sure we do 224 as N times P, which is 0.94, not 216 out of 224, times 1 minus 0.94, what we get is 12.6336. That is slightly, but it is greater than 10. That's all we need. Doesn't need to be egregiously higher, just enough. So, since that is greater than 10, that means we're good. It is normal. We can work with all this. First, we set up the null hypothesis. A null hypothesis is going to be set on our value p. We're looking at proportions. And our null hypothesis is that we assume that it is the same or no different than Chick-fil-A at 0.94. However, she wants to show that, or he or she wants to show that it is more accurate, so greater than 0.94. That's 216 out of 224. That's going to define p hat, the sample proportion. So 216 out of 224. If we run that over here in our calculator, we get 216 divided by 224. That gives us about 96.42%, or 0.9642. Just looking at that value, that is higher than the Chick-fil-A value of 0.94. However, again, our question is going to be, is it significantly higher? If we draw our picture, this is going to be another right-tailed test. We have 0.94 up here. We have 0.9642. And what we're going to find is this p-value. We're going to see how likely that is. To do so, we're going to compute our p-value using our function that we used in the last situation. So we're going to use 1prob z test. So 1prob z test, that's number 5 right there. So I'll write that down. Again, always good to write down the program and all inputs you use, not just 1prob z test. Write down all the stuff you plugged in. P sub 0 here is 0.94. It's the value from our hypothesis. X is 216. N is 224. And what we're looking at is greater than P sub 0. So those are all the inputs I should put in here. If I do that, 0.94, 216, 224, and with the same direction we used last time, we can calculate. And what we get is z, our test statistic, it doesn't ask for it, but it's always good to write it down too, is 1.53. Sometimes it'll ask for the test statistic z. And p, the p-value, is 0.0629. It was given in the description that alpha was 0.05. That was the last sentence in the description. That we wanted to use a 0.05 level significance to test. And unfortunately, p is too big. It's bigger than alpha. What that means that it is far too likely that if we were to reject the null hypothesis, we have about a 6% chance of making a mistake when we really want at most a 5% chance. So it is far too risky for us to reject the null hypothesis in this case. This means that we fail to reject the null hypothesis. Make sure you do know the direction, because it is most likely in cases like this that you will not be given this parentheses hint that you reject if the p-value is less and you fail if the p-value is too big. So in this case, p-value is too big, we fail to reject the null hypothesis. And that is because there is not enough evidence, or there's insufficient evidence to claim that let's see where I can type this. Right there. To claim that the competing fast food restaurant has a significantly higher accuracy than Chick-fil-A. That's essentially what they're trying to show in the alternative hypothesis. Again, I keep repeating this like I did in 10.1, but I still need to. Notice that we are analyzing this by putting what the alternative hypothesis meant in context. The alternative hypothesis, the proportion being greater than 0.94, that is my entire goal here. I want to try to show this. I want to get enough evidence for it. If I don't have enough evidence for it, I still put into context saying I didn't get enough evidence to show this. If I do have enough evidence, then I'll put into context saying I did have enough evidence for that thing. So that alternative hypothesis is our goal, and our conclusions should always be based in terms of that. All right. So got a couple more pages here, so a couple more examples of these. Let's work through them. Good to see a lot of examples of hypothesis tests. In 2000, 58% of females 15 and older lived alone, according to the U.S. Census Bureau. A sociologist tests whether this percentage has decreased today by conducting a random sample of 500 females and finds that 265 are living alone. So we have a few pieces of information there. So 58% of females 15 and older lived alone. That's going to be our original proportion, or P sub 0. We want to see if it has decreased today, so that's going to indicate our direction. And what we have here is a sample of 500, that's our n, finds that 265 of them, that's x, are living alone. Is there sufficient evidence at the alpha of 0.05 level significance to conclude that the proportion has decreased since 2000? So it says again, decreased. All right, so we have to state the hypotheses. Again, there's not a space for it, but we should check their conditions. It does say in the description, let me see if I can move this real quick. Yep. All right, so it does say in the description that there was a random sample of 500 females, so the randomness is met. We're looking at females in the United States, and we only have 500 of them. That's definitely less than 5% of all females, so that should be all kosher. And then the last thing we want to do is check to see if 500 times the original proportion times 1 minus that original proportion, we want to check if that's bigger than or equal to 10. We get 122. Everything seems good. That's way bigger than 10. We have a big enough sample for this. So all the conditions are met. We have a normal distribution. We can test hypotheses. That hypothesis being set up with P yet again for checking proportion, and the original proportion being 0.58. We want to see if it has decreased since then, so less than 0.58 for our alternative. Our p hat, the value that we have, is 265 out of 500. And if we divide that, 265 divided by 500, what we should get is 0.53 exactly. Yeah. If you do 265 divided by 500, you should get 0.53. That is less than 58%. However, again, our question is going to be, is that significantly less? With 0.58 being in the middle of our distribution, 0.53 being somewhere below that, we want to find that proportion down here and see if that is significantly far enough away. Notice as well, our level of significance is really small. Because alpha is 0.01, that means we only want to allow, at most, a 1% chance of accidentally making type 1 error. It means we want to be really sure. Now, because alpha is so small, that means beta or type 2 error is far more likely. So you have to keep that in mind, but we're going to progress through. We're going to compute our p-value and the test statistic technically as well, using, again, one prop z test with our provided information. I already labeled above what all our pieces were. We have p sub 0, we have x, we have n, and we have our direction based on our alternative hypothesis. So should just go to stat, into test, and plug those values in appropriately. All right, so p sub 0 is 0.58, x is 265 out of the total of 500. Notice that those two are always put in that order so that these two should simulate the fraction itself right there. And then what we're looking for is less than. So we're looking for less than p sub 0. So 0.58, 265 out of 500. We want less than that, so we want to make sure that second one is highlighted, and we calculate. We get a z-score of negative 2.27. Again, it doesn't ask us for this, which we call the test statistic, but it's always good to put down. And also we see that negative indicating that it's less than the mean. That means it's good. It should look okay. And it being more than 2 standard deviations does inspire some confidence. However, our p-value that we get here is 0.0117. If I compare that, remembering that alpha was given to us as 0.01 in the description, unfortunately, yet again, p is too large. It is bigger than alpha. That means that we fail to reject the null hypothesis. So we don't have enough information. We failed to reject the null hypothesis. There's insufficient evidence, or there's simply not enough evidence to claim that, in this case, we're looking at females living alone. Yeah, the percentage of females living alone has decreased. That the percentage of females living alone has decreased. Whoa. The percentage of females living alone has decreased significantly from what it once was. All right, yet again, we're saying that we don't have enough evidence to show my alternative hypothesis yet. That's what this statement is, the alternative hypothesis. We don't have enough evidence to show this yet. I am not saying that it is this, that the percentage of females living alone is the same as what it once was. I am saying that we don't have enough evidence to claim that it has changed since what it once was. It is a significant difference there, so make sure you are careful of that. Last example here on page 9. If you have not already, please pause the video and try this one on your own if you did not already do that for the previous one. See how you do, and then come back and unpause the video. So, in 1994, 52% of parents with children in high school felt it was a serious problem that high school students were not being taught enough math and science. So, that is our original value. Right there. That is p sub 0. A recent survey found that 256 out of 800 parents with children in high school felt that it was a serious problem that high school students were not being taught enough math and science. So 256, that's how many out of the total sample of 800. Do parents feel differently today than they did in 1994? And we have our alpha level given to us. Now, since it says differently, that means that we're going to be working with a not equal to sign in our hypothesis. However, before we get to that, we should check our conditions real quick. For randomness, it doesn't explicitly say random, but what it does say is survey. Very often survey does imply random, but we still should address that saying, assuming that the survey that was done was conducted with random samples. So, kind of put the ball in the researcher's court there. We have 800 parents with children in high school. That's significantly less than 5% of all parents with children in high school, even in the United States, or even if I just went to like Utah. It is significantly less than 5%. So we're okay there. And lastly, if we check NP times 1 minus P, where N is 800 times P, which is 0.52 in the first sentence, times 1 minus 0.52, what we get is 199.6. That is way more than 10. So all three conditions are met. We can work with this. For our hypotheses, both are going to be based on the proportion. For the null hypothesis is that it has the same as the percentage from in 1994, which is 0.52. But what we want to show is that it is different than what it once was. This is a pretty good test because this is saying that we're not sure if it's going to be higher than 52% or we're not sure if it's going to be lower. I simply just want to show if it is different from what it once was. Our p-hat value, the sample proportion, is 256 out of 800. That is far less than half. So it looks like the value that we're testing is going to be less than 0.52, but that's fine. 256 out of 800. That gives us 0.32. So we found only 32% of them feel this way now. With the sampling distribution, we have 0.52 in the middle here, and 0.32 is going to be way down here. We're going to find the percentage of this, that p-value. Since we're doing a two-tailed test, what we're actually really showing is we're finding a value that is below it here and a value that is above it here, and seeing what the area and the tails there are going to be there. The area and the tails here should calculate up to alpha. So we really want to see if the p-value is past that, or if 0.32 is past the cutoffs for that tail. So more or less 95% should be in the middle here. Okay. So a little more in depth than I did before. With the information provided, we should be able to run one prop z-test yet again. If you did do this on your own, please make sure that you always write down the program. The first value, p sub 0, is 0.52, is the original proportion. X was 256 out of the total of 800. And what we're looking for is not equal to that value. That's what we're looking for our direction. So we run that stat over and test the fifth option. P sub 0 is 0.52, 256, 800, and we want not equal to, so that first option. We calculate, we get z. Our test statistic is negative 11.32. That is 11 standard deviations below the mean. That is really far below. And that should make sense when we look at our p-value, which says 1.04, but it doesn't just say 1.04, it says 1.04 e negative 29. That means a point followed by 28 zeros and then 104. So 0, 0, 0, 0, 0, dot, 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 dot. It'll be really, really small. So I'm not going to write out all 28 zeros here. That is an incredibly small value. And with alpha being really anything, I think we had 0.05. Yeah, 0.05 level significance. No matter what it really was, the p-value would definitely be less than alpha by quite a bit. That's what we want to happen. Since it is less than alpha, that means we do have enough evidence to reject the null hypothesis. We do reject the null hypothesis. There is enough evidence to show that parents feel differently than they did in 1994 about their children being taught enough math and science. So that's what we have enough information to show. And that's what the alternative hypothesis was trying to show. This again being the alternative hypothesis in context. All right, with that, that's everything for 10.2. Next time we're going to go into 10.3, which will talk about how to do hypotheses with sample means instead and population means. I highly suggest at this point, stop and go and try through the homework for section 10.2 before progressing through into section 10.3. I hope this helped, and I hope you have a wonderful day.